Hello, it's me, Matt Scripps, back after 4 years, your favorite YouTuber, having made some amazing videos such as how to collapse the universe with 2 lines of Python and not 1, not 2, but 3 series that I said I'd continue and I wouldn't stop like the others and stopped each one. But this one is for real. I'm actually gonna make interesting videos now, or at least that's the plan. Anyway, to set the scene, here I was.
Oh my God, where are your legs?
Was in my computing history class, and I hear about this old analog computer called a planimeter. So surveyors would use this, and they'd trace a shape, and for whatever reason, it was able to do some kind of cool calculus with dials because it wasn't digital, and it could display the area of any shape. Didn't have to be a square, triangle, it could be a blob. I want to build that. So that's what we're doing. How hard could it be? Step 1, we gotta buy everything. Here I bought 2 things. I bought this mouse that kind of looks like a pen. This came with some incredible translations as you normally get with high quality goods like the, what do they call this thing? The Lyohi, oh, it's supposed to be lychee, it's just weird font.
Ergonomically posed to alleviate your mouse pain. I hate mouse pain. When a normal mouse instead creates fatigue and discomfort.
I also bought a bunch of these tiny displays that I could use to display the area and any calibration information. Step 2, learn how planimeters work while we wait for shipping. Fair warning, I'm gonna be getting pretty deep into math, and I'm not just talking 1 + 1 = 3, I'm talking multivariable calculus type of thing. I know that sounds scary, and if you don't wanna see it, you can skip to insert time, but maybe if you watch anyway, you'll absorb some knowledge through osmosis. So I'll try not to bore you too badly, but basically when you normally calculate the area of a shape, you would be calculating the area for a triangle, square, rectangle, parallelogram, whatever. I know I just named 3 that have the exact same formula, but triangle is different. So, or even a circle. But what if it's a blob? What if you push in one of the sides of a circle a little bit and it becomes our good friend, the amorphous blob? How are you supposed to figure out his area? Well, something kind of cool that you can do is you can use Green's theorem, which looks like this. While that looks horrifying, when we want to use it for area, we just make a little substitution and bam. Even that may look a little scary, but it's important to note that stretched out S-looking guy with the fashionable belt is basically saying sum up a bunch of really small stuff, and that is whatever has a D in front of it. What this allows you to do is instead of calculating area using a formula, you can now calculate area by tracing the shape. You have that scary looking formula, but we're gonna make it even less scary. The way we're gonna do that, I wanted to get a wand for this, but I forgot. And this is actually the wand of discreteness. And here we have our continuous function, which has the scary looking integral, is actually what it's called. With the circle, it's integral over a closed shape. I don't remember. Anyway, when we take our wand of discreteness and we wave it over by magic, it turns into something even less scary. I'm just now realizing that to someone who doesn't know what's going on, that probably looks a lot worse, but trust me, it's not. But you might be saying, discrete, what does that mean? And it's just like normal math, except you do it really quietly. Hello, it's Matt with a hat here to explain the joke. You see, goddamn. The funny thing is, discrete is different from discrete. Very subtle difference with how it's spelled. Discrete in terms of math means, I'm not really sure what I'm saying here, but it's not correct. That's a horrible example. On to the next. Now that we understand the math, or at least we think we understand the math, closed shape, we can get into the next part, which is actually disassembling the pen. Step 3, disassemble the pen. So I've been taking things apart since I was in probably 2nd grade, and I'm 22 now. This time though, I have 8th grade in the bag. And from taking things apart all these years, you'd think I'd be pretty good at it, but unfortunately this time, I fell for the oldest trick in the book, the screw under the sticker.
Oh, look at that. Classic.
You may see I'm being pretty delicate in the disassembly. The reason for that was I originally planned to put everything back in the mouse case.
Yep, there we go. Let's hope I can find all those pieces.
And when I do get this open, you can see the circuit board and there's one massive chip just out in the open. If I can read the model number off of it, I can find the data sheet, which is basically an instruction manual that tells you how to use the chip, and voila.
See if we can look that up.
If we look this chip up, what do we see? A data sheet.
Hopefully it's in English.
And it is.
CMOS IC for mouse control applications capable of driving up to 3 Alright, this is perfect. This is actually so much better than I could have imagined.
Go back a second. Did you see that? Model number HT6513. And what did we Google? YC1011. This is a different data sheet. Congratulations, you are now privy to this situation of, as we call it, dramatic irony. Step 4, get really confused by a chip because it's completely different than what you think. Optional, but recommended. Unbeknownst to me, the model number is wrong. So I go through all these steps and I try and talk to the chip based off the data sheet that you just saw, but none of it works. Who knows? It's all a mystery. It's literally not, but okay. Beep, boop. Here's the suspicious region. According to the data sheet, that white wire is supposed to output the position, but actually it's soldered to this button, so it doesn't really make sense.
Or if this blows up my computer, but it's okay, I have Apple Care, so.
We're moving the mouse and we're not getting any serial data. So that's not awesome. Nah, still nothing. I don't know why I thought the Flipper Zero has a logic analyzer app, but here I am looking for it anyway. Logic. Oh my god. Everything's falling apart. Rough out here for a flipper. Well, that's too bad. Eventually, I did figure this out, and it turns out it was just a microcontroller that can be flashed with any code. Step 5, we're gonna ditch the mouse and just cut the photo sensor off. I wish I had a video of me doing this, but this was before I found out I can film in the lab. Anyway, so you're just gonna have to trust me. Step 6. Whoops. Step 6, get the display working. I have actually never worked with a display before. I'm pretty sure you learned that in 9th grade, and I'm almost there. But that kind of shows through with how I was trying to get this thing debugged. Here you can see while I'm testing it, it starts scrolling. I didn't know that, so I actually thought it just blew up and I overvolted it or something.
Did it explode?
Eventually though, I did get it figured out and I got the interface made, or at least the preliminary interface, which I kind of edited down the line once I had everything together. Great. So the next question is, what the hell is a photo sensor? So step 7, back to the photo sensor. That's out of order. I used to think when you moved a mouse, it was using some property of how light bends as you're traveling in order to figure out how far you need to move on the computer and in what direction. And when I first figured out how they actually work by reading online, my first thought was, that's a really dumb solution. It almost sounds like something I came up with. But evidently, it seems like it is the best solution. So basically the way it works is, as you see the red dot light up, it's actually lighting up your desk and taking a bunch of pictures with a really small camera, basically. What does that mean? That means when you put tape over your webcam, you should also be putting tape over your mouse because they can see you through that too. Some photo sensors allow you to pull the image off of the sensor and you can actually see what it's taking pictures of. In my case, my photo sensor takes 12,000 pictures per second and compares those. My iPhone 12 has a 12 megapixel camera. That means in each picture, That means the sensor can expose 12 million individual pixels in order to make an image. In my photo sensor, it has 255 pixels. So it's significantly worse than my phone. You would not see yourself taking any valuable pictures with these, but it is super effective in figuring out movement. So now we know how it works, but how do we talk to it? Well, I can find a datasheet off of this and make sure the model number is correct this time, just as we did before. But the problem is that the model number is written underneath the photosensor and the PCB is in the way. And I'm not proud of this, but the solution that I ended up finding, basically, I cut the legs off, I folded it over, I took a picture, I folded it back over, and I soldered all the legs on. I know there was a better way to do it, but that's just the one that I ended up doing. And it works like a charm because I got the data sheet and it was a real data sheet this time. I triple checked the model number and it seemed pretty simple. I had to go through like 4 levels of this website, toggling back and forth between Google Translate because it was not in English. And the data sheet is covered in watermarks, so I don't think I'm allowed to have it anyway. For legal reasons, that's a joke. A tricky part that I didn't really see coming was if you look at this data sheet, it tells you how to communicate with it, but the protocol it uses isn't very standardized. Generally, when you're communicating over wires, sometimes you'll have one wire for input from your computer to the sensor and another wire for output, one from your sensor to your computer. But this one only uses one, which makes things a little strange. The most similar protocol I can think of is SPI or SPI, which uses MOSI and miso, which is almost as delicious as the soup, but instead of being made of broth, it's made of problematic and antiquated naming conventions. Hello, it's Matt with a hat here again to explain the joke. Well, you see, miso is not only a soup, but in the case of SPI, it originally stood for Master In, Slave Out, which of course is problematic. Nowadays, though, I will say a positive twist. There are new potential naming conventions that can alleviate those problems. For example, honestly, there's a million. There's like some people will say student and teacher. Some will say peripheral and controller. There's a million options. So since I didn't have any onboard hardware to communicate with this chip from my Arduino, I had to resort to what's called bit banging, which sounds pretty intense, but it's a lot less exciting than it sounds, unless you're kind of into slow and inefficient communication. Essentially what that means is we're just manually turning a line high and low or putting electricity through it and turning it off, again, manually to send messages to the chip and receive them. This shouldn't be too much of a problem. It actually was a good bit of a problem. So I played around with the bit banging for a little while and I kind of got something implemented. I didn't know that had a barcode on it. Once I had that done, I was able to hook everything up and give it a shot. Unfortunately, even with trying to run the code, as you can see here, I had no success. I couldn't even get the photosensor to light up, but I wasn't getting anything. I set up my camera very optimistically, recording the photosensor and 2 Altoids containers, which is a great way to set things up, would highly recommend, and to no avail. So I figured the first thing that could be a problem would be my wiring. So I went in, I checked it in the lab, I played around, and to my surprise, I found the problem.
Guys, I'm sorry, I couldn't afford the rights to the AI voices, so you're just gonna have to settle for my impressions.
Oh boys, I loves it when all my wirings is correct. Highs, says the reverse polarities guy. I had the plus and minus wires reversed, and this is really bad. But when I was going through doing a continuity test, when I touched one probe to what I thought was the ground on the side I was sticking into the Arduino, and the other probe soldered onto what I thought was the ground on the actual chip, instead of beeping or not beeping, the LED turned on.
What?
So at least then when I would hook this device up, we got it to light up, but I still wasn't able to get any responses. For whatever reason, it seemed like my code was bad, or maybe I had fried the sensor. When I cut the legs off, I even went as fine as to hooking it up to an oscilloscope to look at the individual waveforms, and that actually helped me spot the problem. So as you can see, what happens when we have this line here? Good question. That's the clock line. That says when you see this rising edge, meaning it goes up, you should check what the data is. And you can see that the data is also a rising edge. That's no good because that's undefined behavior. You don't know if it's going to read as a 0 or as a 1. You want it to line up where the clock edge lines up with the flat piece, either at 0 or 1. So was that right? No, actually, it's a total pain. It took me a while to figure out. I was sleeping in my code because I thought that would help me align things, but actually that was a problem. So I took it out and I got this waveform. And for those who don't know, this is supposed to be a square wave. However, we've ended up with a sine wave. Who knows? It's all a mystery. But I'm just going to ignore that because it works. Register 0. Operation read. It's my excited noise. I should have had the camera on. That's photos. Oh, looks like somebody already typed in register 0. Let's do a read operation. Data 30, yeah! Live recreation. Wait, I mean not recreation, original. Step 8, prototype. So from proof of concepts, I knew that this idea worked. I actually did a quick test in Pygame where I just drew shapes, looked and traced the lines with Green's theorem, and it did work. So I went and I made a prototype. In that prototype, I just soldered everything on to header pins so that I wouldn't subject my beautiful KB2040 to eons of torture as a useless prototype. What I needed to do was add in some buttons and a little dial. Now, buttons, super easy to program in Arduino. Easy, right? Yes, that actually is easy. Rotary encoder, however, this thing right here, the thing that spins, that actually doesn't spin very well on my prototype because everything's in the way. It was a pain in my ass. Oh my God, I spent hours on this thing. Anyway, I did find a not very promising chunk of code on the Arduino forum, and by some magical, whatever you want to call it, it actually worked, and it debounced pretty good, so I was happy with it. And that was the fun part. We can actually do some testing. So here, I took whatever piece of paper was on my desk, which so happened to be an advanced linear algebra exam from last semester because I'm lazy and didn't clean my desk. Draw some shapes, just known shapes, measure them, write down everything, and it actually worked pretty good. I was pretty satisfied with the results.
Ooh, that's pretty good. That's awesome. 1.42 inches. I'm gonna add a measurement feature so you can just measure length if you want.
Now to the next part of the video, the enclosure. Step 1, remember how bad at CAD you are. I'm not only terrible at CAD, but also drawing in general. However, I did try and make these sketches of what I want this device to look like. It was seeming like it would be too hard to put it in the original pen case, so I figured I'll just make a new pen case. Step 2, yes, I am restarting the numbering because I forgot to keep going. Plan and buy the right components. So the KB2040 is great, but honestly, it's pretty big. And if I was gonna fit this in an actual pen case, it would take a lot of effort to it would be enormous if I actually tried to put it in the pen case. So I had to fit an Arduino, a battery charging circuit, all the wiring, the shaft encoder, the photo sensor, the display. That's actually a lot of things now that I list them off. But I had to fit all of that in a small pen case. So I had to look online, see if there was anything perfect, and the lucky ducky that I am landed on the beautiful series of microcontrollers, the Seed Studio Xiao. 这是一个很小的电脑，我的电脑也很小，但我的脑不是电了。Oh my God, it's Matt with a hat again to explain the joke. Oh my gosh, he speaks Chinese too? No, not really. I did take Chinese in high school for a little bit, and we learned that computer in Chinese is 电脑, which means electric brain. So this joke in Chinese is, this is a very small computer or electric brain. And then I say, my brain is also very small, except mine isn't electric. I would even say it is not a funny joke and shouldn't be explained, and it should just be cut out of the video. So now that I had a Seed Studio Xiao picked out, I had to decide what microcontroller I wanted. But I got even luckier, and some of the Seed Studio Xiao microcontrollers have a built-in battery charging circuit. So I didn't have to worry about that. I didn't have to wire it, nothing like that. Dead simple. I found a super cheap battery, which was very small, 40 milliamp hours. Absolutely tiny, but it should fit well into a pen case. We're not gonna do the pen case though. Step 3, start making a pen case. Basically just waste a bunch of time because I realized I put a silly constraint on my model. Why does it have to look like a pen? it doesn't really matter where the iris of the photo sensor is, as long as it's consistent. So we could have the photo sensor here and then have a crosshair up here that allows you to look through the crosshair and just have an unobstructed view. Step 4. This is kind of a detour from the enclosure, but to figure out just how much space I had, I assembled all of the parts that I just bought into what I like to call a spaghetti prototype with just wires everywhere. And they're all random lengths. It was honestly really horrible to work with, and I wish I had done differently, and you'll see why towards the end of the video.
I don't know what that's doing there. I thought I did these steps in order, but I guess I didn't, so just pretend.
Basically everything breaks when I do this, but it is what it is. It works. I test the prototype, it's fine. So back to the next step, whatever we're on, like 7 or 3 or something. Step 6. We're gonna iterate on the design over and over and over again. Here I had my initial design, which had a lot of problems. The first being the hole was completely dark that you were meant to look through. I couldn't see anything through it. Actually, that's a major problem. I messed that up. It didn't make sense to have these borders kind of on the side, which just blocked where you were trying to draw. Nothing fit in the case. It just sucked. So my next design, I moved some things around internally, and I scrunched in these sides so that it was a little bit more visible. And in a incredible feat of over-engineering, instead of saying, let's not have a gaping hole straight down the middle of our project, which we expect some light to come in, we're gonna keep that hole, and we're just gonna cut another hole in the side of it and put an LED into it and turn it on. So truly brilliant. I don't know how I got this far in life, guys. That was one of the dumbest things I've come up with, but it's okay, because I realized that after I printed it, and each of these prints is dirt cheap. They're like $2. So next.
Oh, perfect. I made it green.
So we're gonna skip over a couple of my designs and just go to this one. Here, I added this little crosshair up top, which actually is one of the best ideas I've had on this project. This allows you to really precisely follow a line, and I'm super happy with how it turned out. A major issue with this, though, is that the clasps that were meant to hold the top onto the bottom were so brittle because I thought they just had to have a lot of support, so they were just snapping every time. I decided that I would cut in through the sides and add a lot of flex just through the body. Here you can see I tried to do that with a Sharpie, but unfortunately a Sharpie isn't very good at cutting. It just left a mark, but you know, with the next print, I can fix that.
Yeah, I'd let Matt with a hat explain this one, but I just killed him.
And ultimately I ended up with this final. I was super happy with how it turned out. I originally wasn't thrilled about cutting into the body to make the clasps, but honestly, it gave kind of a lot of character to the front. This is it, Creative Commons license, so please don't steal from me without credit. Thank you. Yeah, so I thought this was really nice, but I just wasn't thrilled about all the artifacts I got from regular FDM printing. So I decided to give it a shot with SLS printing. And I'm sure there's other smarter people who can tell you more, so I won't even bother because I don't know anything about this stuff. So here I ended up with my final SLS print. I was super happy with how it turned out, even though the guy at the Makerspace did tell me there are some things I should have done differently between FDM and SLS, but I thought it was good. Definitely for a first attempt. I widened the crosshair a little bit to make it easier, and yeah, that was pretty much it. I wish I had more footage of the final model, but I don't, so you'll just have to pretend. Next. So I guess in my script I stopped doing steps, so I just call this one putting everything together. Here, I have to admit, I made a lot of mistakes. In my previous clip when I was talking about putting together my spaghetti prototype, I got a little JST happy, as we all tend to be. I got this nice JST connector set and was just making connectors out of everything, and it took up way too much space. So it took up way too much space. I didn't plan the internals enough is another problem. The wires were too long. It was just bad. I'm not even gonna lie to you.
So like I made a JST connector for every component except for the shaft encoder, which is one of the 2 components that actually sits on the top case.
Now I was just like, I'm gonna jam everything in, and I'm not proud of that, and I know I should have done differently. when you're putting everything together, my recommendation, at least when you're jamming, is to do it with A, a hot glue gun, and B, a soldering iron nearby to fix the inevitably broken joints from shoving things into place. Please disregard this part of the video. I'm honestly embarrassed by it. So you may ask, how did the final assembly go? And I'll break it down for you. I was explaining to my friend that I was putting everything together today, and she was like, oh, that's awesome, the project's gonna be done. And I'm like, no, there's like a 40% chance that when I put everything together, it all breaks and I have to order new parts, I have to restart, what have you. She was like, oh, okay, that's disappointing. And lucky me, I don't gamble, but I guess I should have that day because I hit those 40% odds, not even likely, but I was still able to do it. So it broke, basically. The main issue was the shaft encoder for the scroll wheel. It had these 3 little like pinholes of metal that you were supposed to solder to. And I shouldn't even say supposed to solder to because you're not supposed to rip things apart from another device and put them in a different device. But I'm sure there was a better way to do it. I just couldn't get them to fit, so I just glued it in place. I'm not even gonna lie, I wasn't disappointed about that because the code for the rotary encoder did not work for the shaft encoder. When I tried to go up with the shaft encoder, it was fine. When I tried to go down, it also went up, except when sometimes it went down. When I was putting things into place, I just really liked how the scroll wheel looked. So I did glue it in place, and initially it was gonna spin, but I think I spun it so much, things got messed up on the inside and it will never spin again. So there I was at a point where you have to set the calibration distance initially for your scale. Because if you're using this on a map, you'd need that. But I didn't have this scroll wheel. Ultimately, I figured out I could just detect movement in X and Y and then use that to input a number. Everything fell into place, except that I messed up this line that made it count X twice and not Y at all. But other than that, it was good. Probably my least favorite part is that I had to trace the perimeter with hot glue to hold everything together, which kind of looks like crap in some places. But the other issue is I can never open it. But maybe that's a good thing because I feel like this device is kind of like Pandora's box, but instead of a bunch of monsters and demons in the box with hope hiding on the bottom, it's a jumbled mess of wires with a battery puncture hazard at the bottom. So maybe it's a good thing this can never open. So there it is, all assembled. Let's see the bad boy in action.
Hi, I don't have access to the green screen anymore. So this is me making a calibration thing. That's the wrong side. Oh my God, it started to look like Among Us. I have to cut that out. All right, here's our blob. All right, we've transitioned. Now we're actually gonna measure the area of Dobby stuck in a glue trap. So here we got our key, which I'm told is 4 inches. For the sake of these things, it's all equivalent. So we'll see how accurate we are. So first you put in 4 and then you select your unit. Here I'm gonna say inches. You calibrate to your key. You do the first point, next point. Bam, now it knows what 4 inches is. I originally measured this by filling it all in and counting all the black pixels and then doing the proportion. Hopefully this hand gesture helps you understand. Ignore that it doesn't always reset to 0, I'll fix that. You can go as slow or as fast as you want. All right, 23.08 and the actual number is 23.346. So I think we're successful here. And just like Isaac Newton intended for calculus to be used, we now know the area of Dobby in a glue trap. All thanks to this planimeter. That's what it's called. All right, I think that should be pretty sturdy. Hopefully you can hear the sink in the background. It's meant to add ambiance. So I started this channel over COVID because I was bored and I wanted to inspire people. And I think I made some of the most boring content on the internet. It's so real though. Oh my God, this isn't gonna work with my laughing. And over the past, I think 4 years, it's been like 4 or 5 years since I've uploaded. A fun fact, I actually finished my bachelor's degree this morning, so yay me. But yeah, in the last couple years, I've gotten really into hardware and maker-focused content, and that's what I want to bring. I love talking with my hands, but I can't really do it with this setup. What was I even saying? Yeah, so I want to make more maker-focused content. I want to build stuff. I have a list of a ton of ideas that I think are really funny.
Each of these is about a sentence, though you probably can't see from there. One of them is, I want to make a Kindle that is made up of many e-paper displays, and you have to turn the page like you would in a normal book. That's maybe not a good example. When I say these things out loud, it sounds horrible. I want to show you that the world is not a black box. You can take apart some weird mouse that you got online, you can figure out how it works, and you can make something completely new, like a planimeter for visual aid. I have it right here. And yeah, that's what I want to do from now on, really, and I hope you stick around for what's to come. I don't know, I just want to build cool stuff, and I hope you guys want to watch that, because I want you to watch that, and I want me to watch you to watch me to build the stuff that you can watch me watch to build to you, to me to watch to you, so you can watch it, and I can build it, and you can watch me watch you build it. No, me build it.
The frick.